Hello, my name is Rod Elmore, and today we're going to look at the probability problems using the rules of probability. What I've found in doing these, it's very difficult to do them because when you read a problem, you don't know which one it is. So the best way is to memorize the rules. Let's take a look at the rules. And we have 5 basic rules of probability. We have 2 for or. The first one, they're mutually exclusive events. The next or is where they're not mutually exclusive, and we learned mutually exclusive is when they cannot occur at the same time. And then 3 and 4 are both ands, and one is and with an independent event and one with and with a dependent. Independent means one outcome doesn't affect the next outcome, and but dependent means one outcome does affect the next one. And number 5 is where you're using the complementary event, and that occurs whenever you find the word at least. So let's try this first problem, and we want the probability. If we throw a single die 5 times, we want to figure out this probability. At least 1, 5. So we're going to throw a single die 5 times, and we want to know what's the probability we'll get at least 1 5 on one of those 5. If you ever played Yahtzee, this is a Yahtzee game where you throw 5 dice at once. But when you break these down, you break them down to individual events. So I would just throw 1 die at a time and then watch it come up. It'd be the same thing. So when you see the word at least, then you look at the formula sheet, and the formula sheet realizes it tells you you can't do the least ones. So how can you do them? Well, you do the opposite, or the complementary events. And on the formula sheet, the event and the complementary event looks like this. This is the event. This is the event not happening with a little line over it. So these are complementary events. They both are going to add up to 1. So if you take this and add it to that, you'll get 1. So how can you find this one if you know this one? You subtract it from 1. So that's what we're going to do. We can't find this directly. So what we're going to do is we're going to figure out what the complement of this is. And what's the complement of at least 1? If you think about that, what's the complement of at least 1? Well, that's correct. There'd be none, right? So this is the probability of no 5 on all your die. So now we're going to take and get rid of our formula here now that we have it in that form. So now we have to find the probability of no 5s each time. Well, that's an and, an and, and an and. Does one affect the other? No, those are, they cannot occur at the same time, so they're independent events. So it's the product of the individual events. So what's the probability if I throw the first die? It's not a 5, 5 out of 6. What's the probability of the next one? 5 out of 6. The next one, 5 out of 6. Because they are independent. One doesn't affect the next one, although some people think it does because they think they're going to surely get something different. But it's going to be the no 5s, no 5s, no 5s, no 5s, and no 5s. Now, if you multiply all that out on your calculator, you get 0.402. And then you subtract them, you get 0.598. So then there's this, the probability is 0.598, or I like to use percentages, 59.8% of the time. And so we were able to use the at least cued us in that number 5 in our toolbox of formulas we use. So that's the key thing. Read the problem and then decide the formula, but have the formulas in your head. And on the test, I will give you the actual formula sheet. So that'll be kind of handy. So let's try a couple more problems. So problem number 2. Now we got a deck of cards. A deck of cards has 52 cards in it, 4 suits of 13 each, and then you go all the way from ace up to king. So let's find these probabilities. So we got a normal deck of cards. The probability of getting a queen and a spade if you draw one card out. You're going to draw a single card out. What's the probability of getting a queen and a spade? Now we actually could figure that out by thinking it through, but we're going to use our formula. We have an and if you looked at the ands on your formula sheet, you're going to be multiplying, and so you look and see how these independent events, if you just draw in one, it's got to be independent. So we got just going to multiply the two outcomes. So we want to find the probability of a queen and a spade. So first we figure out queen, and how many queens are there? There's 4 queens out of 52. And then this is times, because we want one and the other. It's harder to get. And so then now how many spades are there? 13 out of 52. And then we get 1 out of 52. Now we could have figured that out, because how many queens of spades are there in there? There's only 1 out of 52. But that's our and formula. Now what about this one, just as a comparison? The probability of a queen or a spade. Probability of a queen or a spade if we draw one. Let's go take a look at our formulas for or. Well, we've got 2 or formulas. One of them is mutually exclusive and one is not mutually exclusive. So we have to decide, are these mutually exclusive events or not? Can they occur at the same time? Well, they could, because you could draw out the queen of spades. So they're not mutually exclusive. The probability of a queen plus the probability of a spade minus the probability of a queen and a spade. So let's see, what's the probability of a queen? It's 4 out of 52. And the probability of a spade is 13 out of 52. And now we have to subtract the probability of a queen and a spade. Well, we've got that already. That's 1 out of 52. And so if we calculate all that, we're going to get 16 out of 4 plus 13 is 17 minus 1, 16 out of 52. And that reduces down to 4/13. So that probability is 4/13. So you see, when we use an or, we're going to be adding things, but if they're not mutually exclusive, we got to subtract the one. And this should make sense, because this is the one that was counted twice when we did this. So we've got to eliminate it. That's all we're doing, is subtracting it out. So we picked a different kind of problem and we looked at our formulas. Let's try one more. Okay, in this one, it's going to be a little bit different. Read number 3. The probability that a student will be accepted by a college and get a scholarship is 40%. So let me kind of write that down here. The probability of accepted by a college, so we're going to say accepted by a college and a scholarship is 40%, or 0.40. If the probability that they will be accepted by a college is 70%, so the probability of being accepted by the college is 70%. What do we want to find out? We want to find the probability that the student will be getting a scholarship given that they have been accepted. Given that they have been accepted. What's the probability that they will get a scholarship if we already know they've been accepted? So what are we going to do? How are we going to do this one? Doesn't make any sense unless you look at the formula sheet. Did anything in the formula sheet have a problem where you've got a given event? Number 4, if you look at number 4, it's the probability of A and B. Probability of A and B equals the probability of A and the probability of B given that A has occurred. So that's quite a bit different. So we know what and means. That's got a probability that they both will happen. The probability of A is just the probability that A will happen. But this is the strange one. This little vertical line here, the probability B given that, and this occurs because they're dependent on each other. So the probability of A and B equals the probability of A times the probability of B given that A has occurred. Well, we know what the probability of a scholarship and this one is. So this is 0.40. This A and this A are the same. So it's just like this one and this one. So this will be 0.70. And we don't know this one. This is the probability that they get a scholarship given that the college has already accepted them. And that's what we want to know. So how do you solve this? Using algebra, you divide both sides by 0.70, 0.70. So you end up with that the probability of a scholarship given that they're going to college is 4/7. Or reducing that, you get 4/7. So that's a little bit different driven, but it's driven by these words. You'll always see these words in this kind of problem, that something's going to happen given that something else is going to happen. We're going to try one more problem just to help illustrate this kind of an unusual case here. So let's take a look at one more, and then we'll try these on your own. This time I get to do a little artwork. We're going to go with, I always want to be an artist. So we got a bag of marbles, and in our marbles, in our bag, we have 12 marbles. So we got our 12 marbles, and we have 5 blue ones. We have, unfortunately, 3 black ones. That seems silly. And then 4 white ones. Okay, we got 12 marbles. 5 are blue, 3 are black, 4 white. Find the probability that if 3 marbles are selected at random, they will all be black. Probability of all black. If we pick 3 marbles. So think about this one. As you think about this, think about which one is this? What do we want to do? How are we going to do it? Which one of our 5 rules applies? So first is it doesn't have that thing, the probability of one given that something else has happened. It's not really tied in to make that a complicated one. So it's going to be one of our other problems. Is it an and or an or problem? You got to decide. Is it an and or an or? Well, let's see. We want to pick all black. We're going to pick 3 times. So we want, it's really could be said, you want a black and a black and a black, right? So you want, it's an and problem. If it's an and problem, then you have to figure out, is it independent or dependent? Is it independent or dependent? Well, let's see. If we pick one black marble out of there and don't put it back, that's going to change it. So they're they're dependent events. So now we just have the product of the individual events happening. So what's the probability that the first marble will be black? Well, there's how many black ones? 1, 2, 3 black ones. So it's 3 out of 12. What's the probability the second one will be black? Well, there's one already gone, so there's only 2 left, and there's only 11 marbles left. So this is dependent. So then the next one will be, there's only 1 black one left, so it's 1 out of 10. So that's the probability of all 3. Now that's not going to happen very likely, is it? It turns out when you reduce this, it's 1 out of 220 times. So 1 chance out of 220 that you reach in there and you pick out the 3 black ones out of this group. And this is an and problem where it's dependent. So you have to reduce it. And so now try some of these on your own, but the key thing is when you're doing these is read the problem, look at your 5 rules, and then decide which one of the rules to use and plug it in. If you do that, you can be real successful. If you just read them and emotionally think about them, you're not going to do very well. So try the homework and try all the homework on these so that you get good at picking which rule to use. Thank you.